Great. So we're very happy to have Alex Takeda, and he will be speaking about non-commutative Legendre transform and Calabi-Yau structures.
Hi, everybody. Thanks, Manuel, for inviting me to give this talk. Thank you all for coming. I just wanted to start by saying if anyone has any question, feel free to just interrupt me and or write in the chat, but I can't see the, while I'm sharing screen, I can't really see the chat window. So also feel free to just tell me that there's a question in the chat if that's the case. So I'm going to talk a little bit about some joint work that I have with Maxim Kontsevich and Yiannis Vlassopoulos. This is actually related to a project that these two had for a long time, and sort of I picked it up, and I just want to tell a little bit about some new perspective on it, and explain a little bit how it has to do with non-commutative geometry and the Legendre transform. And then hopefully at the end, I can talk about some applications. Okay, so let me start by, before talking about any of these generalizations, just talk about the ordinary Legendre transform. So a quick reminder on the Legendre transform. So if you remember this from like physics or classical mechanics, it was something that, you start with some convex function and you're on the line, and you end up with another convex function on the line. But it turns out you can also do this on vector bundles. So you can generalize this to the transform of vector bundles. And it's something that for now only works fiber-wise. So we only care about each single fiber of a vector bundle on at a time. So what does it do? It goes between, let's say, fiber-wise convex function on some vector bundle E. And this transform relates this to the same thing, fiber-wise convex function on E dual, right? So E was some vector bundle, which real vector bundle with fiber Rn over some manifold. And let's say I have a function on my vector bundle. So I'm going to call this normal L. And this is to remind you that in physics, this would be kind of the Lagrangian in classical mechanics, right? So it's you can think of E as being the like position and velocity, for example. So how do you do the Legendre transform? I'm going to separate into 3 steps. So the first step is you construct a map that I'm going to call fiber-wise derivative. So this map, I'm going to give it in coordinates just because it's easier to see. So it's a map from E to E dual. And it's a map that sends, let's say I have a point X on my manifold in coordinates V1 through Vn. It's a map that sends this point to the same point on the manifold and dl dv1 through dl dvn. So you can think about it as being like sent to the graph of the derivative of L. Okay? So easy fact that if L is a convex function, then this thing is a diffeomorphism. And so there exists some inverse, FL inverse, right? Second step of taking the Legendre transform is I'm going to take L and I'm going to write the energy function. Right? So this is another function and on E itself. So it's a function on E to R. And this function is, you're going to recognize this formula is VI dL dVi minus L, right? So if you remember this Hamiltonian formalism, this is going to give you the Hamiltonian. But right now I'm calling it the energy function. And then the third step is you combine these two things. So you write down the Legendre transform. So now so let's see, Legendre transform of L is, I'm going to denote with this like fancy L of L, or H for Hamiltonian. And this is, you take this function, EL, and you precompose it with the inverse of FL. Right, so FL goes from E to E dual. So this thing is a function, this function H is a function that goes from E dual to R. Right? And another way of writing this is that the value of H at a point is the critical value over, over V of V times P minus Lx of V. So P, so the V is the coordinates on E, and P is the coordinate on E dual, right? So this is a function of P. Right, so what are some facts about this transform is that if, let's assume L is convex enough. So if L is convex, some facts, we have that H is also convex, fiber-wise. And if you take its fiber-wise derivative, it's the inverse of the fiber-wise derivative of L. And if you take this transform, you recover L. So it's involution. It leads you back to functions. And another fact that if you take the induced map on functions, right? So this is the map. So H was a map, sorry, FH was a map from E dual to E. So the induced map on function goes from functions on E to functions on E dual. I'm using O here, it doesn't mean holomorphic, it just in general means functions. And this thing satisfies that H, this pullback is, I'm going to be a little sketchy here, but it's the variational derivative of this Legendre transform as a function of F at this function L, right? So it's saying that if you now you know your Legendre transform, if you vary your function a little bit, you can understand the variational derivative by looking at its Legendre transform, the Hamiltonian, and looking at the map induced on functions. Okay, so this is the usual commutative version of the Legendre transform. Eventually, what I want to do is want to describe a non-commutative version of this. But as a stepping stone, I'm going to describe a supercommutative version of this. So section 2 is odd Legendre transform. So by odd, I mean now instead of E being a vector bundle, I'm going to take E to be a so odd vector bundle. So now let me take E to be the shifted tangent bundle of M, sorry, shifted cotangent bundle of M. And therefore E dual is my my shifted tangent bundle of M, right? So what this really means is that I'm only going to work with functions at the level of functions. So the algebra functions on E is the functions on the shifted cotangent bundle, which are polyvector fields. So this is exterior algebra of tangent fields on M. And I'm going to write these as so this is a set of things. I'm going to pick coordinates. So it's going to be f0 of x. So there's some constant part. Then there's some degree 1 part, alpha I, plus some degree 2 part, alpha I, alpha j, right? So alpha here is the d dxi. So these are the vector fields. So I'm going to pick some coordinates on M, just do locally and write it like this. So it's some non-commutative algebra because the supercommutative algebra because these are odd, so the anti-commute. Right? And similarly, the functions on the odd tangent bundle are just forms on M. So these are just your usual forms. And I'm going to write each form also as being a function of x plus some degree 1 thing with beta I plus etc. And now beta I, sorry, let me keep some index consistency here. Beta I is my dxi, is my basis of one forms. Right? And if I, so these is, let me focus now on the polyvector fields. So for a polyvector field is a sum, a general polyvector field is a sum of many p vector fields. So if I have some number p, I can express a p vector field and then pick coordinates on it. So let's say I have this vector field, big P is equal to 1 over p factorial, p I1 through ip, alpha I1 through alpha ip. So it's a sum of terms like this. And before we took derivative, before on the commutative case, it took derivative with respect to the fiber coordinate. So we want to do the same thing. But now the fiber coordinate is this odd variable alpha. So you have to define what we mean. And if you think about what it should be, I'm gonna say if you define d alpha in of this product, I1 through IP, this is equal to p minus 1 to the n times the same product, but now you omit the in. Right, so it's some extension of this the derivative to this non-commutative variables. Okay, so now I have this function of the fiber and have the derivative. And I'm going to do the same thing with the Legendre transform. So, we started with the convex function, and what's the equivalent of a convex function here? We're just looking locally. So it's a function that has a non-vanishing degree 2 part, right? It locally looks like a parabola. So let's say I have gamma is my polyvector field. Polyvector field, and let's say for simplicity that it has no without constant or degree 1 terms. So it starts in degree 2, and so in degree 2 is gamma 2ij. This is some function of my coordinate on the manifold, and let me put this factorial factor over here, alpha I alpha j plus gamma 3 ijk over 3 factorial alpha I alpha j alpha k, and so on. And each one of these is a real value tensor. So this is a matrix, and this is a rank 3 tensor, etc. And my version of convexity, at least around 0, is going to be that I'm going to assume this thing is non-degenerate, right? So this thing is full rank. So some invertible matrix, right? So okay, so let's try to repeat exactly the same thing we did with the Legendre transform. So there is steps 1 through 3. So step 1 is fiber-wise derivative. So remember that the fiber-wise derivative that we had was before it was a map from E to E dual. And now since we're working on functions, we just have my fiber-wise derivative defined as a pullback from functions on E dual to functions on E. And how do I calculate this? I say, well, I write the equation beta I is equal to d gamma d alpha I, right? This was the relation given by, we're taking dl dvi. So I'm doing the same thing, but in non-commutative variables. And if you just use the way we define these derivatives, you get that this is some function of some expression that lets you express the beta i's as a function of the alpha i's. So each time you change these factors because of the rule we had over here. Right? So this gives a way of expressing betas in terms of alpha. Right? So if we have a function here, which is a expression in betas, we just plug in this right-hand side into it, and then you get an expression in terms of the alpha. So you get a map of algebras like this. So that's the equivalent of a fiber-wise derivative. And if gamma 2 is invertible, we can invert it too. So gamma 2 is invertible. We also get an expression of the alpha i's as some expression of the beta So there's some linear term, there's some quadratic term, etc. And this matrix M is the same as the inverse of the matrix gamma 2. So you get an inverse manifold of algebras. Okay, now that's step number 1. We describe in terms of functions.
Alex, can I ask a quick question?
Yeah.
Yeah, just a sanity check. So you keep saying non-commutative variables, but we're still in the graded commutative case.
Yeah, sorry, graded commutative. Yeah.
Okay, good.
Super commutative,
Yeah.
super commutative, yeah.
Yeah, okay.
Right, super commutative. Eventually, they'll be all non-commutative, but now super commutative. Okay, so step number 2 is write down this energy function. So energy function was my E gamma. Remember, it was I'm going to use some summation conventions. So it's alpha I, d gamma, d alpha I minus gamma, right? Before it was vi, dl, dvi minus l. And if you calculate what this is again gamma 2 ij over 2 factorial times alpha I alpha j plus now 2 over 3 factorial gamma 3 ijk alpha I alpha j alpha k, etc. And by this I mean that is the same expression as gamma, except that you start at 2 as before, and each factor is multiplied by p minus 1. So in fact, in this graded commutative, in this example at least, it's easy to calculate the energy function. Each p form just gets scaled by p minus 1, by a factor of p minus 1. And in 3, now we invert, right? So we calculate the Legendre transform. By that, we say let's say we're going to obtain some lambda. So this is going to be my Legendre transform of gamma. And by definition, it was this f, sorry, my f gamma inverse of E gamma. Right, so what I mean by this is you first you take this expression, and then you replace alpha I by the expression we deduced before, alpha I equals mij, beta j, etc. Right? So and then you get some expression in terms of form. There's going to be some lambda 2 ij beta I beta j plus lambda 3, etc., etc. So you get some form. So this is something that maps between a polyvector field and a form. So now we have a proposition that this polyvector field gamma satisfies some integrability condition. So this bracket is this Schouten IHES, I can never pronounce this name, bracket. So this is some bracket that exists in the polyvector fields and that generalizes the brackets on vector fields. So this gamma satisfies the condition if and only if the form lambda is closed. Right? So this transform maps between integrable polyvector fields and closed forms on the other side. And this is something elementary. You can just check using the formulas that I wrote. And now there's some generalization. So now suppose the gamma instead has a degree 1 term. So it has a gamma 1 I alpha I plus gamma 2 ij alpha I alpha j. So what does this mean? Before, not having any linear term meant you were sort of at a critical point of this function gamma, right? Like the bottom of a parabola. Now, if you add a gamma 1, your parabola is sort of tilted. So if you think about what it means in terms of the Legendre transform, it means you also shift the coordinate on the dual. So this has the effect that you shift this dual coordinate instead of beta I, you shift it to beta I is beta I tilde is equal to beta I minus this gamma 1. So adding this linear term means you shift the coordinate on the other side. And then the proposition, there's a corollary of the proposition above, that what? Maybe it's a different proposition, another proposition, that this new gamma satisfies this the integrability condition if and only if lambda is not closed, but it vanishes under this shifted differential, right? So we shift the round differential by the Lie derivative with respect to gamma 1, and this is almost true. The 0 plus higher order terms in. Let me write 0 plus O of maybe gamma 1 squared. So gamma 1, high order correction gamma 1. But morally, at least formally around a certain point, it's true. Okay, now that we've discussed this odd version, I want to talk about how to generalize this to a non-commutative version, and that's going to have something to do with these Calabi-Yau structures, right? So before we had, so gamma was just to recap, gamma is a polyvector field, and it has this bracket. And on one side, and on the other side, you have this lambda, which is some form, some differential form. And you have this funny shifted differential. You have a differential d minus d of gamma 1. So to find the non-commutative version, I'm going to think about some non-commutative object that has something that looks like polyvector fields on one side and something that looks like a differential form on the other side. In the non-commutative setting that I'm going to use is this idea of Kontsevich and Soibelman of using a Kontsevich and Soibelman of using a infinity algebra as a non-commutative space. So maybe put into quotation marks because this has to be interpreted in some way. So, if you have a commutative space, you can think about sort of the algebra functions on it. And this says, let's just toss out the commutative space and just think about the more general structure, this A infinity algebra, instead as a replacement for a non-commutative space. Well, just to remind people in the audience, what's this non-commutative, what's the A infinity algebra? So if you have, let's say, quick definition. So A is some, let's just say Z-graded vector space. And I'm going to vector space with some field K, and I'm going to always work in characteristic 0. And A is endowed with a bunch of maps, mu n from n copies of A to itself of degree 2 minus n under this grading, right? So if you have if n equals 2, then it's just some kind of product. And this product doesn't satisfy associativity relation on the nodes, but instead it satisfies associativity relation up to some mu3 and mu4 and so on and so forth. I'm going to take n to be greater or equal to 1, so there's no curved infinity algebra structure, and the relation satisfied by these satisfying the relation. So I'm going to write very schematically. If you compose, sorry, you put plus or minus. This field has minus signs everywhere. I'm going to omit them in this talk just because it's too much to write. Right, so some relation, if you compose mu in all possible ways with appropriate signs and sum of everything, you get 0. So if you think about what this means for mu2 and mu3, it says that mu3 it gives you a homotopy for mu2 being associative, mu2 not being associative. Okay, so they propose to model the space as a non-commutative space, and now we have to think about what this means in terms of this, what the polyvector fields and what the differential forms with this funny differential look like in this formalism. So let me start with the right-hand side, actually, the differential form. So here we need something that looks like a differential form, and that has kind of two different differentials. One of them that looks like taking Lie derivative with respect to a field. So to describe this, I need to talk about something called Hochschild homology and cohomology. So Hochschild homology and cohomology. So this is some theory of invariance, originally of associative algebras, but you can extend it to A infinity algebras. Let's say, I'm going to quickly make a sketchy definition here, that Hochschild homology of A, you should think about as being the kind of left-derived tensor product of A with itself over a bimodule, as a bimodule over A, right? So if you think about what this means underivedly, you get the zero Hochschild homology. So what is zero Hochschild homology? It's just A tensor with A over itself, not derived. And this is just A modulo its commutator ideal. And the way I'm going to calculate this for, let's just say for an associative algebra, this would be simpler, is calculate the Hochschild homology of A by some explicit complex, by some explicit complex. Complex C of A with some differential, which I'm going to call B. Right, so this is as a complex is at each step is just a tensor product of copies of A. And the differential is if applied to some simple tensor A0 through AP, it collapses. Let me put tensor so it's easier and clearer. It collapses two by two of these simple tensors. Right? So this is minus A0, A1, A2. Sorry, there's plus or minuses everywhere depending on the degree of these things, and then up to AP A0. Okay, so then we have the Hochschild homology of A is the homology or cohomology of this complex. Because I'm working with homology and cohomology together, I'm going to grade everything positively. So you see all my differentials are going to these differentials are going to the right. So I'm going to write cohomology. So this B, this Hochschild differential B is going to be is going to take the role of this Lie derivative with my gamma 1, and this is because it can be thought as because B can be thought as Lie derivative with respect to mu, where mu is my this collection of maps, my infinity structure. So sorry, I'm maybe this doesn't make much sense for people that haven't seen this theory of Hochschild homology before, but there are actions of I'm getting ahead of myself here. So another thing you have is now Hochschild cohomology, which is Hochschild cohomology, which is some sort of in some sense dual theory to this in some contexts. But I'm gonna I'm going to also take this to be the cohomology of some explicit complex. And this complex is Hom from some copies of A to Hom. Etc. And there's some differential that's described in a similar way from this one above, right? And there's an action of Hochschild cohomology onto Hochschild homology, which I'm gonna give explicitly by an action of the chain complexes. So this is action, which is there's actually many actions. There's some action of degree 0, which I can think of as being the, how do you call this thing? When you have a vector field and X and you take inner product, is that what it's called for the vector field? Contraction.
Yeah.
Contraction. And there's also a degree, I guess, 1 action, which minus one, maybe minus 1, yeah. Degree -1 action, which plus 1, -1, depending on which direction it goes, which I'm going to think about as the Lie derivative, right? And under this action is this is true. This B is the Lie derivative with respect to this structure. Right, so we already know what the Lie derivative here is. Now we just need to come up with a version of the de Rham differential. And the de Rham differential is going to be given by the cone differential. So for simplicity, let me just say, assume A is strictly unital. Then there is some cone differential, which is a differential of degree -1, B of degree -1, which sends A0 through so differential acting on Hochschild chains of A0 through AP, which just puts this 1, the element 1 in the beginning. I'm cheating a little bit here for this to be actually true, we need to take a certain quotient of the complex, but let's just pretend it's true. So you put 1 in the beginning and then you sum over all permutations of this complex, right? A0, etc. So this B is going to take our role of the de Rham differential. De Rham. Right, so we kind of know what it's supposed to be. Our version of forms with this funny differential is going to be Hochschild chains with some shifted differential. And the version that's going to appear is going to be this thing called negative cyclic homology. So negative cyclic homology is we take, so I'm going to denote a certain chain complex like this. And this is I take my Hochschild chains, and I take many copies of it. I'm going to shift these copies and by adding a certain variable of degree +2. So I just do many copies of Hochschild chains. And I'm going to combine these two differentials, one of them that has degree +1 with another one that has degree -1 by adding this, by using this variable u, right? So this is going to be our equivalent of analog of differential forms with this funny differential. Okay, so so we know what one side is, which is our differential forms. Now for the other side, which is polyvector fields. So I need something that extends vector fields, which I know to be Hochschild cochains, and has a certain bracket that extends the bracket on Hochschild cochains. And the analog is going to be something. The analog is going to be something that we described in a previous paper with Maxim and Yiannis that they also had been working on for a long time. And I'm going to call this higher Hochschild cochains. So because I'm getting kind of near the end, I don't want to spend too much time defining what it is, but I'm just going to make some drawings. So so usual Hochschild cochain you should see as something that takes many inputs of valued in A shifted by 1 and outputs one thing valued in A. And so this is the usual Hochschild cochain. This is the usual Hochschild cochain. And a higher Hochschild cochain is going to be something that the same way that a single vector field has only one ddx, polyvector field has many ddx's. Our analog is also going to have many outgoing things. So this one should be the analog of like a 4 vector field, for example, and it's something that takes in many copies of A shifted by 1 and outputs some number of copies of A. So I look at all these types of vertices, and I'm going to put them all together. So I'm going to make some definitions here. If you take for any integer L, I'm going to define the higher L Hochschild cochains of A to be this kind of vertices of this type. So it's Hom from, you take some number of copies of A shifted by 1, and then you take some number of copies of L times, and then with L outputs. And then you take a product of all these things over all possible N1s through NL. So I'm just gathering all these vertices by the number of outputs and adding some appropriate shifts here. And this thing has a Z mod L action that rotates the vertex. Right, so I'm gonna, my analog of a polyvector field is going to be graded invariant of this action, right? So I want something that looks like a function of x times some vector dx, another function, etc. But I want an invariant under the cyclic permutation. So to do that, I'm going to make another definition. If you choose for any integer D, I'm going to choose, I'm going to make a version, like a D shifted version of a polyvector field. So define C, let me square brackets D, A to be, sorry, to be just the sum, again, the product over all L greater or equal to 1 of this thing, the CL A, but with some appropriate shift, dl minus d minus 2l plus 4, invariant under this Z mod L action. Right, so what is an element of this thing? It is a choice of a bunch of maps like this for any number of outgoing things. And then proposition, the bracket on ordinary Hochschild chains of A extends to a bracket on this big thing, on C, sorry, I'm going to shift it by 1 just so it's a bracket of degree 0, to a bracket of this thing. And to describe this bracket, it's I can just describe in drawing. So if you take a bracket of some, let's say, some alpha and beta, this is going to be some sum over all possible ways of drawing a vertex beta and then mapping it into a vertex alpha with appropriate minus signs, and also vice versa. So here alpha and beta both have 3 legs, for example, and you see the outgoing thing has 5 legs, right? But extends to a bracket and so a bracket which gives DG the algebra structure, DG the algebra structure. Structure on this this space, right?
Alex,
Yeah.
so there's no Gerstenhaber's or there's no cup products here in these higher Hochschild,
There's no cup product.
right? Or
I
maybe there's a version
don't
of it.
know. I don't know how to define the cup product because you kind of have to define on which sector you're going to input your chain, you know?
Right.
The same way that if you try to define a cup product with like a polyvector field, you have to define which one of the vector fields to pair with. Yeah.
Okay.
I don't know how to define the cup product, but the bracket extends to this DG algebra structure. So this is going to be, this big space is going to be our equivalent of polyvector fields. And you might complain that the space looks very huge and how would you ever write one of those things? But turns out we have a way of writing them in a bunch of cases of interest by using some obstruction theory. But anyways, so remember that before we had this integrability equation, m bracket m was 0. Sorry, gamma bracket gamma was 0. Right, so we're gonna have a similar thing here, and this is something that appeared in our earlier work, which is a definition also by Maxim, me, and Yiannis Vlassopoulos, is that a pre-Calabi-Yau structure on M on A is a solution to this equation, to the equation m bracket m is equal to 0 of degree 1 in the DG Lie algebra. And I guess because I have a a D here is of dimension D. So if you choose a D, you look at pre-Calabi-Yau structures of dimension D on A, then there's a solution to this equation of the form. So M is starts with my A infinity structure. So this is my A infinity structure that I fix. You don't have to fix it, but I'm just going to fix it. Plus something in with 2 outgoing arrows, plus something with 3 outgoing arrows, plus etc. So in particular, if you have a pre-Calabi-Yau structure M, then by taking one part, you get a infinity structure. And in general, this kind of thing is interesting. We define this kind of thing to deal with algebras that are not of finite dimension, or not even compact or smooth. So the structure is sort of very general and can exist on many of these really big algebras. But in the case when A is when A is finite dimensional, actually this structure is nothing new. So there is a bijection between this dimension D pre-Calabi-Yau structure on A and cyclic A infinity structure structure on A plus a dual shifted by 1 minus D, such that A is a sub A infinity algebra. Right, so in the finite dimensional case, A pre-Calabi-Yau structure is just a cyclic infinity structure on the sort of doubled A, right? So the commutative picture should be something like a pre-Calabi-Yau structure is not a symplectic structure, but it's like some deformation of symplectic structure of M inside of a T star M, something like that.
So
Okay.
was this notion also defined by Tradler and Seinalian? Is that right?
Yeah. Sorry. There's a lot of things in this field that have been defined by other people in the past. So this has appeared as I think they called the V infinity algebra.
I think so.
Or
Yeah.
something of Tradler and Seinalian. So yeah. So in their case, this is exactly the same structure. Someone correct me if I'm wrong with exactly the name, but I think they call it V infinity algebra for vertex. Right. Okay, now since we're getting kind of to the end, I just want to give the statement of this non-commutative Legendre transform, and then if I have a little bit of time, I can explain how to obtain it. So this is a statement, it's a theorem. Let A be some smooth A infinity algebra. So this means this homological smoothness condition. Well, before I say this theorem, let me say something first. Let me just define some notation first, it'll be easier. So I take any A, right? And I produce this space CD A, which is where my pre-Calabi-Yau structures live, right? And I'm gonna call a subset of this to be my kind of moduli space of pre-Calabi-Yau structures. So this is just this sits inside of here. This is the space of solutions to that equation, right? And inside of the space, I have like an open subset, which is the space of solutions such that M2 is non-digit. So M2 was this thing with 2 outgoing legs, right? So there's M2 is 2 outgoing legs. is non-degenerate. I didn't explain to you how to define this non-degenerate condition, but the point is that uh, M2 lives in some space that can be identified with homomorphisms of A bimodules between A and some kind of dual of A. So this is a bimodule dual of A. And this non-degeneracy condition is saying that this map is invertible. Right? So I'm going to call this ND for degenerate.
A
Okay,
priori,
now I'm ready to.
I can think of this M2 as a element in A tensor A or something, or A dual tensor A dual or something like that, or not?
You can think about it in
Like,
yeah, you can think about it in so this is actually to for these equalities, let's just say A smooth.
mhm.
Yeah, so this you can identify this with A dual tensor over A with A dual. Yeah, but the non-degeneracy condition is easy to see if you express in terms of the homo bimodule. It just means the homo is invertible. And now I can state the theorem that there are maps, I'm going to call L and phi, and that go between some subset of negative cyclic chains of A, which are also non-degenerate in some way, and this space of D pre-Calabi-Yau non-degenerate, right? So and that are inverses in some way. And this thing arises as some sort of non-commutative Legendre transform. And this thing is some sort of inverse of it, some quasi-inverse that you can pick. Right. There's also a relative statement, but I don't want to mention that one because it's gonna take some time. But maybe I should just say a little bit why this map should be a Legendre transform. By the way, these sort of have names. So things on this side are people call smooth Calabi-Yau structures. And this on this side is some non-degenerate pre-Calabi-Yau structure. Right. Okay, so I'm gonna go to the full hour if you don't mind. Is it okay?
Yeah, of course. Yeah.
So how is this a non-commutative Legendre transform? So remember that the Legendre transform we obtain by doing this like three-step procedure. First, write the fiber-wise derivative, then you write the energy function, and then you invert it. And this map we get by doing something similar. So the first step is to write down the fiber-wise derivative, right? So the fiber-wise derivative should go from this space to this space, right? So my fiber-wise derivative, so I fix M is my pre-Calabi-Yau structure. And my fiber-wise derivative Fm is something that goes from kind of a tangent space to this space, which I'm going to identify again with just with negative cyclic chains. And to a tangent space of this thing, which if you think about this space and its obstruction theory, you should think about as the complex that is this linear space lives inside, together with the differential that's taking the bracket with n. Right? So to produce this map, there's no sort of map of spaces to take a derivative, but we just produce a map that behaves like fiber-wise derivative, and we produce it explicitly. So produce this one explicitly by using some formalism we call the ribbon quivers. which is some directed version of these black and white graphs of white graphs. Graphs of Vol and Westerland, following some work of Costello. And other people had also worked on this. Sorry if I don't mention everybody, but it's but we have some directed version of these. And the space we're looking at is a space of these kind of ribbon quivers that you should think about them as parametrizing a surface that has one closed boundary, a circle boundary, and a bunch of open boundaries on the other end. That can be in or out. And this in. So this should be, it should be something like you input your smooth Calabi-Yau structure here, and you get some kind of vertex on this one. But practically speaking, what that means is that we produce this Fn by defining a bunch of sequence of graphs, gamma 2, gamma 3, gamma 4, and so on. So these are a bunch of these ribbon quivers. In gamma 2, for example, I can write the graph explicitly is some linear combination, some symmetric linear combination of graphs like this. So there's some way of taking this graph with the arrows and inputting some Horseshoe chain inside of this X, and then getting something that has two outputs, which is what we want. So in the end, our our vertex is given by the two outgoing things is given by gamma 2 applied to gamma 0, with three outgoing things is given by gamma 3. There's gamma 3 component 1 applied to component 0 applied to gamma 0 plus some other graph applied to gamma 1. These are all components. Lambda components of my some negative cyclic form. Anyways, there's some way of producing from a negative cyclic form a bunch of these vertices, and then we do the other two steps. So we write down this energy functional. So starting from M, we write down some energy function. This step is easy. Just like in the odd case, we set energy function of M, which is just sum of what am I doing here? Mk multiplied by k minus 1. So you just scale each one of these mk's. And in 3, we just invert. So we define the Legendre transform. Define this Legendre transform of my structure M by taking this fiberwise derivative, finding some quasi-inverse, and applying it to this energy function. So of course, in this case, because these are, you have to find a quasi-inverse, you need to make some choices. But you can sort of coherently make all these choices. So this is how we define this map L, which goes in this direction. And then you can show by some induction argument that you can, in fact, reverse it and produce also an explicit map phi going the other way. So in this case, in this smooth Calabi-Yau case, there's some version of one-to-one equivalence on both sides. And to make that precise, you need to say exactly what is the equivalence relation on either side, but it's something quite natural. Okay, I think I'm out of time, but.
Okay, so let's thank Alex. So any questions or comments? I have a quick question, so I can maybe start. I think I missed what so the domain of this phi, it's negative cyclic chains or is it, yeah, this, what does this mean? Is this like, it should be a chain complex, right? So it's not,
Yeah, yeah. That's right. That is the negative cyclic chains.
and what's this D for?
Oh, it's just integrity. It's just integrity.
So how are you thinking of this as a chain complex if you're just looking
Oh
at,
yeah, sorry. That's a good point. The D shouldn't go here. Yeah.
okay.
Yeah, this map depends on D because it lands on a different chain complex, but in fact it is.
Right, okay, good, good. So it's not,
It's just that later when you take this, this one is correct because then this goes from things in degree D to D Calabi-Yau.
I see. So this first, okay, so this this statement is not, this quasi inverse on the left is not right then, right? You wrote Q inverse.
Yeah, yeah. It's a little imprecise. It is another map. It is. Let me put some quotation marks.
Okay.
So the what happens here is that the left hand side is it is there's a natural notion of equivalence relation, which is just just homology, right? If you two chains, they can be homologous. And but the right hand side, this pre-Calabi-Yau, moduli pre-Calabi-Yau structures, that's not a linear space, right? You can't add two of those. So the right notion in here is actually equivalence under some action of some gauge transformation, and this has a structure of some groupoid. So the statement of level sets should be between negative cyclic homology and like a set of orbits under this gauge action.
Okay.
Yeah, so that's what I mean when I say that the inverse is in some way that's a little more complicated than saying quasi-inverse, because one of them is a linear space, the other one is not a linear space.
Yeah, but FM is a chain map. That's below.
FM, yeah, FM. This one is a chain map.
Yeah, and that uses the previous formalism of the previous paper of you and Kontsevich and Vlassopoulos, then, right?
Yeah. So FM is a chain map, and yeah, I guess I didn't mention this, but in the beginning, I had a story about how if you take the factorized derivative and the map into some functions itself is some variational thing. So you should think about this as being the map on tangent spaces, right? So this is at a certain point you have also a tangent space, and you map to like a tangent space in this. Yeah, but so this is the chain map is some linear thing. Maps between like the tangent complex at what point in this space and a tangent complex at point in this space.
Okay. Questions? Ralph?
Yeah, I sort of a remark and a couple of questions. So first of all, your Lie structure, that just follows from general theory of dioperides. I think you're looking at planar dioperides here. So for any of those things, you get a standard bracket. I'll send you some reference. And then the second thing is then you're looking at a master equation, although somehow there's a D missing. And so that's a remark. So that is sort of a well-known story that this bracket exists. And also the shifted one. And so then I have sort of two questions. So usually it's the things you get as solutions of the master equation are the same thing as things for the Feynman transform. There's a one-to-one correspondence. There's just for the quantum master equation, it's maybe like Baranikov, and then for the general case, I'll also send you the reference. So the right-hand side sort of usually is related to the left-hand side with the Feynman transform. So is there anything you can say about this negative cyclic homology, which is like a Feynman transform? Is that obvious?
So yeah, so there's something I'm a little bit confused, but I think so there's a statement that if you have a solution to the quantum master equation,
right,
you have another thing that is a closed form, right?
Yeah.
And somehow that statement relies on having this BV operator.
No, not really. So that's what I was saying. There's just a completely general theory, but you have to, the BV operator comes
Yeah. So
from the fact.
the statement that I know, it's you kind of take dual twice, right? Because you use like a certain measure to define the BV operator. So in this case, we end up with things on dual spaces, right? On polyvector fields and
Yeah, but that's the general story. We should discuss another point. You can look at the theorem. So the BD operator comes from sort of a self-doing, which you don't have. So that's for modular operands. What you have,
yeah, that's true. I don't have a self.
What you have is so you only get a bracket, and the bracket you get from a dioperand structure. Now yours is kind of interesting because it's a one. That's why you only see the cyclic groups instead of just the full permutation groups. I guess, that's what I'm guessing. But
yeah,
this is just a quadratic thing. So you're going to get a master equation, and that's the master equation. And then the Feynman transform does take duals. So algebras over the Feynman transform are sort of duals. So
okay.
they exactly work with dual spaces.
Yeah,
it is exactly going back and forth with these dual spaces. It's not completely, there must be something. You can ask Maxim, he should know because, Baranikov was a student and you're working with him.
Yeah.
So he should know.
He knows in a way that perhaps takes me a little while to.
Right. No, I'm just saying, that's interesting. I didn't know that. So that just suggests that, so that's the question. That suggests that your negative cyclic homology is related to the Feynman transform of planar dioperants, which is.
Yeah, I would, I don't know how to take remove like taking modules over the operand and state this in terms of just the underlying algebraic structure, but that would be interesting. Yeah, I just don't know.
Yeah, right. As I said, you can read and we can discuss some other time. And then the second question is, I'm curious to the map you have. So the second question is like two parts. It's like part A is, do you have like a field theory for this, or didn't you think about it in that terms?
You mean which map? The FM?
Yeah, you have the sort of the sum over graphs and particular graphs, and usually if you have a sum over graph, that's sort of a field theory.
There's
exponential of some s, and you're writing this s down.
The interpretation is that so where these graphs come from, you sort of look at this. You look at this thing, right? The moduli of surfaces with like at the tube, right? You have one incoming thing and a bunch of open ones.
Right.
Actually, that space, you know what it is? It's a space homotopic to S1 because it really only depends on the marking on this.
Right. Yeah. Sure.
And right, so you the gammas are a representative of a particular class, which is on a class of a point on this S1 modular rotation, which is just a point.
Okay, that's interesting. Yeah, because it's very close to the stuff that I looked at with Bob Penner on this open.
Yeah, so if you want like kind of less explicit description, is you take you have an action of this moduli space, you take another differential that implements this quotient, and then you have one class. You really only have one class to a non-trivial class, and these gammas represent this class.
Okay, interesting.
But Alex, but there's a statement in your first paper, right? Which is maybe like the Hochschild chains of a pre-Calabi-Yau algebra have a structure over a DG prop. Right?
Yeah, that's a statement. I didn't have time to write here, but
right, and then that DG prop is described in terms of these graphs, and that extends what Natalie and what Ralph have worked on in some way, right?
In the case when A is finite dimensional or compact,
exactly
the same is the same statement.
Right.
Yeah, but as Ralph commented, I never want to take duals of A basically, because I'm allowing A to be infinite.
Can I ask a little more about that? So what sort of examples? Your abstract mentioned something with the base loop space and.
Yeah. So one example of something that is smooth but not compact is you take A to be chains on the base loop space of some manifold, right?
Yeah.
And so that's not that's not that's not compact, but it is homologically smooth, and there is a smooth Calabi-Yau structure in it when M is orientable.
Yeah.
Right. So you could input this structure into here, and you would get a pre-Calabi-Yau structure on this algebra, and you get a bunch of these operations.
Which should, in theory, be related to string topology, right, or something.
Which in theory should be related to string topology. I don't know if you can recover everything from string topology, and this is something I've been thinking about and also talking to Manuel about. And I think there's a little some more you need to put besides just the smooth Calabi-Yau structure on this thing.
So you don't have a clear description of what you get it yet. Is that what you're saying?
No, I don't. Mostly because the formulas are true, but they're sort of very big, and I think if you I would need to have a better control of the which terms appear to understand. So
but I'm confused. How does this relate to? So that's an example of one of these algebras you're looking at. But how is your theorem useful in here? I mean, what do you? Yeah.
Oh, so this theorem, if you take this, then you would get a pre-Calabi-Yau structure on A, which would give you an action of this prop on Hochschild chains of A, which are quasi-isomorphic chains on the free loop space. So you would get a bunch of operations on the free loop space.
I guess this statement you did not write down. This might be the.
This is a different statement. That's what
Yeah.
what I'm asking. What do you? Yeah. So
yeah, it's a different statement.
That's a different statement. If you have a pre-Calabi-Yau structure, then you get this proposition.
Exactly.
Yeah.
But what about the theorem that you did state? What does that say?
Well, it says that you can explicitly write down all these M's for
all the possible pre-Calabi-Yau structures.
Well, you can write all the possible, but starting if you have one smooth Calabi-Yau structure given by an trivialization of orientation bundle of M, for example, you would get a bunch of these M's.
Yeah, I guess what's not clear to me, maybe along these lines, is this higher Hochschild cochains. When A is the chains on the base loop space, what's the meaning of that, right?
Yeah. So I can write down some more things over here. So if there's also another thing we proved that if A is smooth, then if you take these higher, let's say L higher Hochschild cochains of A, this is quasi-equivalent to Hom of A bimodules from A to this is A dual, but tensor over A L minus 1 times. Right. So in fact, if you only care about things up to quasi-equivalence, then if your thing is smooth, these are just all these groups are the same, right?
What's the differential on the left-hand side?
The differential on the left-hand side is a differential. Yes, differential.
Bracketing with
only with the A infinity structure.
Oh, I see. Okay, so
yeah, that's right. So if you care about these only up to bracketing with the infinity structure, all these groups are they're all the same if my A is Calabi-Yau. Right?
Yeah, I don't have any immediate interpretation of that right thing for chains on the base loop space on a manifold, though. Yeah.
Can I ask another question? So on your graphs, you had these annuli and one closed input and the other one is open. And that was there a direction on the open one? So closed was in, and then the open ones were all out, or any
configuration, because
any configurations of ins and outs. That's interesting.
Well, because you need to give all these maps, right?
Right, right. Because I mean, it looks like
but in fact, you can sort of forget that you can sort of the same way we did before of gathering everything by the number of outgoing legs. You can sort of also gather all the graphs and then kind of forget the incoming legs.
Because I was sort of I mean, it looks a little bit like if you just have an open closed theory, which is just a Frobenius algebra instead of an A infinity one, then there is a map open to the closed part and the other way around that you also need for the Carty condition. That is sort of the flute thing where you have one open output or input and one closed output and input. So you're doing like the multi-to-one version of that.
Yeah. So yeah, I guess So in that case, I think it is some sort of dual version of this.
Yeah, and then my question was: is it like an open-closed interpretation of this kind of thing that you're sort of saying the closed part is a deformation of the open part or something?
Yeah, well, I guess the statement, which is also about the first paper that I didn't mention, is that if you have this pre-Calabi-Yau structure, which you can see as a it's just open information, right? Just modulo over some open thing. Then there is a kind of extension to the open closed theory that maps a closed string to this to Hochschild chains.
And that's the map, though. That's what I'm asking. The one you give here from the cyclic to the.
Yeah, I guess that is the map. Yeah.
Okay.
I have another comment, another example, which I think it should give an example for Natalie and Ralph. Can you go up a little bit?
Yeah.
Where you wrote like A plus A dual shifted by 1 minus D.
Where did you put that?
Here. Where was that?
Oh yeah. Sorry. Here.
And the correspondent, here. So this, look at the right hand side. So if you, this like the Tate Hochschild thing that I worked out with Shengfeng gives an example of something that looks like this. Right now, you have to put A to be Hochschild chains on a Frobenius algebra. And A dual will be Hochschild cochains on that Frobenius algebra. And now we constructed a cyclic A infinity structure, but the problem is that of course, the pairing is not non-degenerate because these are infinite dimensional. Like, it's non-degenerate with respect to certain filtration with like Hochschild length, right? Length of monomials.
Yeah. But
it's not non-degenerate in general. So I think that gives an example of a pre-Calabi-Yau structure.
Yeah, but it's not entirely obvious, right? Because this statement that I wrote only assumes the pairing is
non-degenerate. Right. Yeah. But I mean, my guess was that since you're defining pre-Calabi-Yau structures to remove this non-degeneracy condition.
Yeah, maybe it is possible. Yeah.
Maybe that gives an example of an honest pre-Calabi-Yau structure. But in any case, it's some kind of cyclic A infinity structure on this cone. This looks like a cone, right? Like a
maybe.
Like a mapping cone. If you have a map,
like a mapping cone.
Yeah, a map of degree D.
I guess for a symmetric Frobenius algebra is literally the mapping cone.
Symmetric Frobenius algebras, exactly.
Yeah, symmetric Frobenius algebra is literally the mapping cone. Yeah, I'm sorry if I rushed. If I got rushed near the end, it's just that
that's good.
I noticed I was running out of time. But
yeah.
Of course, if any of you want to talk about it, we can also chat separately or.
Any other comments or questions? This still does not give the Goreski-Hingston thing, right? The
I don't know how to produce
the DG
is that
the prop action on the Hochschild chains of a pre-Calabi-Yau algebra that you guys have, right?
It's going to be some sort of moduli space of surfaces type thing. Is that what?
I think so, right?
Yeah, I think you need a slight modification of this, and also because you don't actually expect to have a product that's coherent over all of let's say all of chains on free loop space. You always need to map your model by something.
Yeah, you mean the Goreski-Hingston thing?
The rest of it,
Yeah.
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 Yeah. Yeah, so I think it is some variation of this story, but I don't know exactly.
Any other comments or questions? No? If not, let's thank Alex again. Thank you.
Thank you for coming. Thanks for inviting me again.
Yeah.
Thanks.